Alright, let's look at this problem called last day where you can still cross. This is something that we have already done once, and we did it using BFS or DFS and using binary search. This time we'll do it using disjointed set union or the union find. So let's still go through the problem again. So basically we are given a grid, and initially everything is land, like so 0 represents land, 1 represents water. On each consecutive day, a new cell changes from land to water. So essentially a day equals to 0, everything is water. At the final day, I mean it only shows this, but at the final day everything becomes water. That's how the thing is. And so we have to find out the last day where you can go from top row to bottom row. The last state is possible to walk from top to the bottom by only walking on land cells. You can start from any cell in the top row and end at any cell in the bottom row. You can only travel in the 4 cardinal directions. So what we'll do here is discuss the approach using disjointed set union. And the idea here is so going from left to right, what's happening? One land converts to water. So you can also say other way around, going from right to left, one water converts to land, right? You can also sort of do it like that. So what we'll do is we'll go from right to left when everything is water. When everything is water, you can't go from top to bottom just using the land, right? Because there is no land. And then you'll know what was the state of the previous day. So for example, let's take this example. So 0 0 0 0, that is the first state, and then 1 0 0 0 is the second day, 1 0 1 1 is the third day, 1 1 1 0, and finally you'll have this state, right? So we start from this state. Okay, so we start from this state, and we know by looking at so the cells of RICI, it tells which on this day which cell converted from land to water. Like this was a cell that changed, right? So that means on the previous, by you knowing that, we know the state of the previous day, right? So what we'll do is we'll keep disjointed set union, and we'll change this to this as we go forward. So we'll go from right to left in that direction. And for example, here you can't reach, I think I converted something wrong, 1 0 1, it was 0, yeah. So on this day it was 0 0, and on this day now we look at this cell, and we connect it to all the land cells, right? So we'll use this union find algorithm, and finally we want to know if the top row and bottom row is connected. How do we find the top row and bottom row is connected? We can add another cell, for, a cell named top and a cell named bottom, and if if you find a land on the all the land cells on the top row will be converted to the top node, all the bottom cells on the all the land cells on the bottom row will be connected to the bottom node. So that's the idea, and we'll use this union find. So first let's define the union find algorithm. So uh, let's quickly write the code for union find in general. So you have a class, let's call it union find. You have a public a constructor. You want to define the size, right? So what's the size of union find? Whatever will be passed. What do you keep? So obviously we need to add the optimizations for union find. So you use weighted union find with path compression. That's what you're gonna do. So you wanna keep root of each you want to keep the root of, so a root and a rank for each node. Let's initialize it. So root equals to new int size, and so rank equals to new int size, I equals to 0, less than size plus plus. Root of I, so it's everybody's root is itself. You need to know the union find. So I mean, I'm just repeating the classic union find algorithm, but that's something that we're not covering how it's done, but sort of have to know about it. uh, Rank of I equals to 1. This is your classic constructor. Now one of the operations that you want to do is you want to return the root of, or the final parent of, you know what, let's not call it root, let's call it parent, right? And you find the root of so you want to find the, it's like a forest, it's like a tree, and whatever is connected, it's if they're in the same component, they will be on this in the same tree with the root. So you want to find that root of the tree. So you go if x equals to x, return x, else you do alright. So this is what you're doing, path compression, and now you do public, now you want to do union. So void union x and y have to be union. So you first find root of x, and root of y equals to this. Now if rank of root of x is greater than rank of root of y, then you make the root of y as the child. So you go parent of root of y equals to x, else if rank of root x, if this is less than y, then x becomes the child. So root of x equals to y, and if then you can choose anyone. So let's use this, and rank of this guy will increase. Now this is your union with the weighting based on the rank, which is essentially height of that tree. And maybe let's define another function, boolean, let's call it connected, or x and y connected, and we say if their roots are same, then they are connected. Now let's talk about the time complexity of union. So in union what we are doing is we are connecting the two. We are doing a find though. So tick tick tick. So basically both union and find, the time complexity is, I don't know how to print alpha, but it's essentially log star n. It's the Ackermann function or something, I don't remember exactly. Almost constant. That's the benefit of it, is that you can connect and you can find if they are connected and all of that in sort of constant, like pretty much close to constant. It's not really constant, but pretty much close to constant for large, like 10 to the power 5, 10 to the power 6. It's quite constant, like up to 5, 6. That's how long it goes. So now what we'll do is, for each cell, we'll create and we'll consider, and we want to add a top and a bottom. So we'll take uh, union find. We'll call it disjointed set union equals to new union find of size row times column. We'll add 2 extra. The reason for adding 2 extra is because um, we want to connect all the land in the top rows to some node, so that we don't have to check for each land row and each bottom row and check if they are connected. Just connect them to a top and a bottom, something like that, right? Like a separate node for a top row fully and separate node for a bottom row fully, which are lands. So that's that. Now let's define the grid that we have. So on the last day everything will be water, so everything will be 1. So uh, make everything as water. And now we go from right to left. So I equals to cells dot length minus 1, I greater than equals to 0, I minus minus. What we're gonna do is, okay, so first you want to get the row and column. So row equals to cells of I 0 minus 1, because it's 1 based, convert into 0 based. So if I 1 minus 0. Alright, so this is your row and column. So first you want to convert it into land, so convert it into land. Also let's define top and bottom. So you added 2 extra rows. So let's say the index of the top node is 0 and the bottom will keep it at so row times column plus 1, right? So you have 0 to row times column plus 1, 1 to row times column is the actual cells, and 0 is the top row and bottom is, and this row times column plus 1 is the bottom. Okay, so now what you do is, if this row is equals to 0, you do disjointed union set dot union. Okay, first let's get the cell. So cell, how basically you want to convert it into a 1D array, sort of like 2D array. So how do you represent? So you go whatever is the row, those many columns plus the column number, right? So you convert it basically 2D into 1D. So 0 1, basically you're reading this as 1, this is 2, this is 3, this is 4, like that. Okay, so for example, if I am at here, I'll do, or rather let's look at a different example. Let's take this. So if I am at, let's say here on this guy, so this is the row number 1, right? Row number 0. So row number 0, okay, this is row number 1. So 1 times 3, already 3 cells, plus interesting. Column plus this column, and you do a plus 1. Or what you can do is, you can, reason for this plus 1 is because you want to keep them from 1 to row times column, right? Yeah, so this is fair. So this is your cell, and then you want to do, yeah, that's it. So this is your cell. Now So you want to connect cell to top. If it is the last row, then you want to connect cell to bottom, and you want to connect it to all its neighboring lands. So all its neighboring lands is, let's define the directions. So let's just do it like that. Minus 1 0 1 0 0 minus 1 0 1, and so for each direction and direction you get this. New column equals to c plus director of 0 direction of 1, sorry. So what is the new cell in 1 dB? So you wanna say new r times the number of columns plus the column number here. Let me think. Wait a second. So if I was doing 0 best, I would say 0 1 2. 3 4 5. So you don't need this plus 1, right? It's already 1 base. So for example, yeah, it's already 1 based. This is already 1 based, except if r is 0. Yeah, it's confusing to me. No, I think it's fair, right? So if you are on row number 1, then you start with 0 1 2 3, correct? Yeah, so you need a plus 1. So that's fair. You do a plus 1 here, and then what? If this is in the grid, greater than or equals to new row is less than row less than column, and the grid of new row new, okay, it's not new row and new column. If the grid is equals to okay, don't do this land, you make it converted to land means you convert it to 0. So if it is 0, then it's a land and a neighbor, so you want to connect it like that. And here if you see, if connected, if top and bottom finally gets collected, then you return this I, else you return 0. Compilation error, let's fix it. Number 67, uh, what happened? Why is everything wrong? Okay, 3 got 2, 3 got 1. Wait, hold on. Expected output is 3, expected is 2. So in the first case, 0 1 2 3, so you had everything as water, and on the last day you convert it into water. And if there are more waters, yeah, obviously it has to be I minus 1 plus 1, so it has to be I. Similarly 0 minus 1 plus 1, so it has to be I. All of that is fine. There is a mistake. I got it. This is wrong, I think. Does it look like it's just returning second last always? So 1 2 3 4 5 6 7 8 9. Obviously the last one. So 0 1 2 3 4 5 6 7 8. So basically what's happening is this connected is becoming true. So top is 0 and bottom is this, which is fair. Now this is the second last stage. You connect, it's a bottom also connected to bottom. I think some mistake in this calculation, I feel like. I0 I1 0 1. So your index is, your zero base index is your row number times a column. So if your row number is, for example, 0 1 2, so you will start from 6, 0 1 2 3 4 5 6, and then plus column. So that's your zero base indexing. You want to make it one base, so you do plus 1. I don't see any problem at all. Let's check union find if there's a mistake in union find. There was a mistake, huh? Okay.